In number 5, we are given a reaction with 2 amounts of reactant, so this is a limiting reactant problem, but it also asks us to calculate out the grams of excess reactant, and it asks us whether or not the reaction mixture will be acidic, basic, or neutral once the limiting reactant has been consumed. So this reaction is the reaction of an acid and a base, and so we have some sulfuric acid reacting with some sodium hydroxide. So sulfuric acid is an acid, sodium hydroxide is a base, and so depending on which one is the limiting reactant, the one that remains in excess is going to cause the solution to be either acidic or basic. The only way the final solution would be neutral is if these reactants were put in the exact right amounts to react fully. And so we're going to first distinguish which one is the limiting reactant, and then from there we'll be able to determine whether the reaction mixture, once the reaction is complete, is acidic, basic, or neutral. So let's start by writing out the reaction. So sulfuric acid is H2SO4. It's reacting with sodium hydroxide, NaOH. And so we're going to end up with 2 products here, a salt and water. So our first product of water is going to be HOH, and remember we re-crisscross hydrogen with hydroxide on the product side. Our second product is going to be the salt formed when sodium bonds with sulfate. So that'll be Na2SO4. Now we do need to balance this equation. I noticed right away there are 2 sodiums on the product side, so I'm going to go ahead and put a 2 in front of sodium hydroxide on the reactant side. Now that gives me 2 hydroxides, so I'll put a 2 in front of water, so I have 2 hydroxides, and that actually balances out the hydrogen as well. I have 2 hydrogens and 2 hydrogens on the reactant side. So this is a fully balanced equation now. So let's go ahead and calculate out, figure out what our limiting reactant is, and then from there we'll be able to then calculate the theoretical yield, the amount of excess, and so on and so forth. Now, in terms of theoretical yield, it's asking us how many moles of water will be produced. We actually don't need to go all the way out to grams. We can stop with moles of water in this particular case because it's only asking us for our theoretical yield in moles. So let's go ahead and start with 875 milliliters of 6.2 molar, and I'm going to go ahead and convert to liters before I start my dimensional analysis. Just move the decimal point 3 times, so 0.875 liters, and then the 52.3 grams of sodium hydroxide. It's not a molarity value, so we'll just start going to grams to moles. So let's see, 0.875 liters of H2SO4. We can go ahead and take our liters to moles using our molarity value of 6.2 molar. This is a high molarity value, 6.2 moles per 1 liter. Now that we have our moles of H2SO4, we can convert moles of H2SO4 to moles of our new substance, which it's asking us to find the number of moles of water, H2O. Then we'll set up a similar conversion for our sodium hydroxide, but for the sodium hydroxide we actually get to start with grams, 52.3 grams of NaOH. And so this is a more familiar conversion. We start by going from grams to moles, moles to moles, and then we will have our final answer. So grams to moles. And sodium hydroxide has a molar mass of right about 40 grams per mole. Then we will go from our moles of NaOH to moles of water. Notice I haven't filled in any numbers yet. I'm going to come back and do them all at once now that I have my setups yet. I haven't filled in any of my mole ratio numbers, I should say. So for my moles of H2O in both, I will put 2 moles of water on top. For my moles of H2SO4, there's no coefficient, so I know that a 1 is implied. And for my moles of sodium hydroxide, there's also a 2 in front of sodium hydroxide. So now I have my calculations all filled in, so I'll go ahead and calculate out the moles of water that can be produced from both of these amounts of reactant. Now remember, whichever one produces less will be our theoretical yield, and the reactant that produced that amount, our limiting reactant. So for the H2SO4, if I multiply this whole thing out, I get 10.85 moles of water. And then for the sodium hydroxide, if I multiply that all out, I get 1.308 moles of H2O. And so the amount from the sodium hydroxide is definitely going to be our theoretical yield, because this is far less than the amount of water produced from the sulfuric acid. So our limiting reactant is going to be our sodium hydroxide, meaning that all of the NaOH gets used up, and our excess reactant is going to be the acid. So our final reaction mixture, before we even calculate out the amount of excess that remains, we know that our reaction mixture is going to be acidic. Reaction mixture will be acidic. And this is because there's a lot of excess acid left at the end of the reaction. And so that's one of our answers, that our reaction mixture will be acidic. We've answered the last part. Now we just have to calculate out the exact number of grams of excess reactant that we have. And this is going to be a little bit tricky, because we aren't actually given an amount of grams that we start with, so we're going to have to convert our molarity and our moles into grams to figure out how much is left. So we're going to have to make 2 conversions here. First, I will convert the excess amount into grams. So we'll start with the 0.875 liters times the molarity, 6.2 moles per 1 liter. And then 1 mole of H2SO4 is equal to some number of grams of H2SO4. And if I calculate out the molar mass of H2SO4, it's about 98.1 grams per mole. Okay, and so if we start out with 0.875 liters of H2SO4, that's 6.2 molar, we end up, that is equivalent to a mass of, if I multiply this out real quick, that gives me a mass of, let's see, 532.19 grams. So let's write that out. 532.19 grams of H2SO4 available. This is the amount we have in the beginning. So now we have to determine the amount that actually gets used up. So I will come down to the bottom of the page, and I'm going to use my limiting reactant, my theoretical yield, the 1.308. And I could also start with my amount of my limiting reactant. I could start with this value, or the mass that's stoichiometrically equivalent to both of those. Anything stoichiometrically equivalent to my amount of limiting reactant. I'll start here with moles of H2O, and I'm going to work backwards this time to figure out how many grams of H2SO4 were used up. So we'll go from moles of H2O to moles of H2SO4. And then we'll do one more step to go from moles of H2SO4 to grams of H2SO4. And we already calculated out the molar mass as 98.1 grams. We need to get our mole ratio from the chemical equation. 2 moles of water are equivalent to 1 mole of H2SO4. Okay, this is a lot of math here, but when we multiply this out, we get that there are the amount of H2SO4 that's used up is only 64.157 grams of H2SO4, and this is the amount that's used in this reaction. So the last step is just to do a little bit of subtraction and figure out of the 532 grams that are available, how much is still left once we use 64.157 grams. So our excess is equal to 532 grams minus 64 grams. And I am going to go ahead and round to just a couple sig figs here, because in our final answer we're going to have we can only have 3 sig figs in this answer here, and so I'll round that to 3, which means my final answer will just be a whole number answer here. So 532 minus 64, let's see, 532 minus 64 gives us a final answer of 468 grams of excess acid. And it is this excess acid, remember, that is causing our solution mixture, our reaction mixture, to be acidic in the end. It's because we have all of that excess acid. So make sure you box all of the answers here. We answered how many moles of water will be produced. Right here, there's our moles of water. We answered how many grams of excess reactant remain. It's down here. And we answered, will the reaction mixture be acidic, basic, or neutral? And it will be acidic. So it's important just to make sure that in these problems you answer all of the components.